Let's talk about Coulomb's law. We'll start by talking about the computational part of Coulomb's law, and that's the formula that you see here. This formula is for the magnitude of the electrostatic force, the F sub E, that exists between two charged objects, Q1 and Q2. Notice that we're using capital Q's, so that means we're dealing with the magnitude of the charge, which makes sense because, again, this formula is for the magnitude of the electrostatic force. K is Coulomb's constant, that's 9 times 10 to the 9th Newton square meters per square Coulomb. And R is the distance between the two objects. Specifically, it's going to be between the centers of the two objects. Now, this is the computational part of Coulomb's law. It's the formula. Notice, though, that it's for the magnitude of the electrostatic force. We already know that force is a vector. So that's where the conceptual side of Coulomb's law comes in. It lets us know how to determine the direction of the electrostatic force. So here are my two objects, and I'll just label them 1 and 2. And what the conceptual side of Coulomb's law tells us is that objects that have like polarity, or you might say the same polarity, are going to repel. So here I have two positively charged objects. They have the same polarity. They are going to repel each other. So that tells me the direction. How does it tell me the direction? Well, what we mean by repel is to go to go away from the object, so exactly away. So that does not mean any old direction, it means this direction. This is the force, the electrostatic force on object 1 here. And it has to be directly away from object 2. I wouldn't have it go this way. That's not directly away from object 2. It has to be the way I drew it initially. And at the same time, 2 is repelled by 1, so it has to go directly away as well. And that's the electrostatic force on 2. And they're repelling each other because they have the same charge. It wouldn't matter if they were both negative. I said the same charge earlier, I meant same polarity. Because they have the same polarity, they're repelling each other. It wouldn't matter if they're both negative or both positive, they're going to repel. Now, if, however, we look at a different situation, let's look at a situation where they have opposite polarity. If they have opposite polarity, then they attract. And now I know, since they're attracted to each other, that's the force that's going to be on object 1, the electrostatic force, and object 2 is attracted. And it's directly towards the other one. It's not at some angle, it's directly toward. These are the only possibilities in both situations. Again, like polarity, or you might say the same polarity, they have to repel. Okay? But if they're opposite polarity, they attract. And that's how you determine the direction of the electrostatic force. And consequently, then you can deal with the vector nature of the electrostatic force.